Today we're going to be talking about finding limits, and limits really are the language of calculus. So I've got the notation down here in green. I would read this as the limit as x goes to c of f of x equals L. This is basically telling me that if I go to this graph of f of x and I approach x values of c, both from the left and from the right, the y values are approaching L. Notice that a limit doesn't give you information about what happens exactly at x equals c. Instead, it just gives you information about what happens near that point. So it doesn't matter whether c is undefined or not. We're only interested in the behavior as we approach that point or as we get arbitrarily close to that point. So let's create a table of values to illustrate this concept. If I want to find the limit as x goes to 0 of e to the x minus 1 divided by x, that limit is referring to a function, the function e to the x minus 1 over x, and that limit is asking us what is happening to the y values as the x values are getting closer to 0. Now, notice if we actually plug in 0 for x, e to the 0 minus 1 divided by 0, I end up getting 0 divided by 0, which is actually undefined because we can't divide by 0. So if we're to plug in 0 into this function, we get something that's undefined, and I'm going to indicate that in my table of values. But with limits, it doesn't matter what happens exactly at x equals 0. I only care about what happens when I'm close to 0. And so I used a calculator to help me out with this, but I'm basically creating a table of values. And so I plugged into that function that was given to us, negative 0.1. So e to the negative 0.1 minus 1 divided by negative 0.1. I put that into a calculator, and I got approximately 0.9516. And then I'm going to do the same for the rest of these given x values. And when I plug in negative 0.00001, I actually got 4 9s followed by a 5. And so it looks like as I approach x equals 0 from the left, it looks like these y values are approaching 1. They look like they're getting closer and closer to 1. Now I plugged in those positive x values as well. I plugged in positive 0.1 in for x, and I'll fill in the values I got from my calculator. So when I plugged in positive values of x that got closer and closer to x equals 0, it looks like those y values also got closer and closer to 1. And so for that reason, we would say that this limit equals 1. So the limit as x goes to 0 of this function f of x equals 1. Again, it doesn't matter what happens exactly at 0. With limits, we only care about what happens as we approach 0, as we get close to 0. For my next example, we're going to try to answer some questions about limits graphically using a graph. And so first of all, I need to give you a little bit more notation. When you see limit as, say, x goes to 1 of a function, that means we are approaching 1 from both the left and the right. We want to approach x equal 1 from both sides. However, if you see a little plus sign next to that 1, just like this, limit as x goes to 1 with that little plus sign, that actually means we're only approaching x equal 1 from the right. And finally, if you see a limit as x goes to 1 with a little minus sign there, that means we're approaching from the left. Okay, so let's try to do some problems here. We have a graph of a function f of x, and we're going to try to find a bunch of limits using this graph. So part A says we are approaching x equal 1 from the right, and so I go on this graph. If I approach x equal 1 from the right, it looks like the y values are approaching 2. So this limit is going to equal 2. Part B has the little minus sign. So now we're approaching x equal 1 from the left, and those y values appear to also be approaching 2. Because both the left and the right sides line up, because your left and right-handed limits are the same, that means your two-handed limit is also equal to 2. So if you approach from both the left and the right, you get a y value of 2. And in fact, I could even add another part to this. It turns out at x equal 1, f of 1, so exactly at that point, the y value is also equal to 2. Now, we're not always going to get the same answer, and let's just move on to my next point to see an example of that. If you printed out my notes, you can see what these next examples are, but rather than scrolling the page down, I'm just going to do my work over to the side. So if I want to find limit as x goes to 2 from the right, so I go to the graph on the right side of 2. If I approach x equal 2, it looks like my y values approach 3. The same is true if I approach from the left. If we approach x equal 2 from the left, the y values also equal 3. Because my left and right-handed limits are the same, both equal to 3, then the two-sided limit is also equal to 3. Now, x equal 2 is a little bit different from x equal 1 in that there is no point at x equal 2. We would actually say the function is undefined there. However, notice that doesn't impact the limit. The limit doesn't tell you anything about what happens at a point. It only tells you what happens when you're near a point. Okay, what happens at x equal 3? Well, as I approach x equal 3 from the right, so if I approach that point from the right, the y values approach 1. If I approach from the left, the y values also approach 1. Because those two numbers are the same, the two-sided limit is also equal to 1. However, at x equal 3, if you actually find the point with an x value of 3, it's up here. It has a y value of 2. Again, notice that the function value doesn't impact the limit. The function value tells you where the point is. The limit tells you where the curve is, what happens when you're close to that point. Okay, let's do one more. What about x equal 4? As I approach x equal 4 from the right, the y values approach 3. But now, as I approach x equal 4 from the left, the y values approach 2. Because these two limits aren't the same, because the two sides don't line up, we say that the two-sided limit does not exist. And you can abbreviate that just as I've done as D and E. So again, anytime your left and right limit are not the same, your two-sided limit doesn't exist. However, if we were asked to find f of 4, well, f of 4 is the point down here, and that has a y value of 1. So once again, the limits tell you what happens as you approach a point. They don't actually tell you where that point is. All right, let's do one more example. Finally, we can be asked about limits as x goes to infinity. And basically, this is just asking us about the end behavior of the graph. This is asking us what happens as we go to the right side and the left side of the graph. So as x goes to positive infinity, that means I look at this right arrow. And this right arrow appears to be flattening out at y equals 3. So this limit would be 3. This means as x gets large, the y values approach 3. A limit as x goes to infinity also gives you information about a horizontal asymptote. Because my limit equals a number equals 3, that actually tells me that I have a horizontal asymptote of 3 on the right side of the graph. The left side of the graph also has a limit. If I look at the left arrow, that would be as x goes to negative infinity. It looks like those y values are approaching 0. So that means my limit is equal to 0, And that also tells me that on the left side of the graph, I have a horizontal asymptote of y equals 0. All right, so the main idea here is with limits, you're interested in the behavior near a point, not at a point. So that's it for today. Next time we'll talk about how we can find limits algebraically without graphs and tables. But please let me know if you have any questions.